Welcome back. Let's practice solving multivariable optimization problems. All right, so here's our first example. We want to find three positive integers whose sum is 30 and the sum of the squares is a minimum. Okay, so in this problem, the value that we want to optimize is the sum of the squares of three positive integers. Specifically, we want that sum to be a minimum given that the sum of those numbers is 30. Okay, so the regular sum of the three numbers being 30 is what we would call the constraint for this scenario. We want to minimize the sum of the squares given this restriction or constraint. And so to solve this optimization problem, we have to make two different equations. We need an equation to represent the sum of the squares, or the value that we want to minimize, and we need an equation for the constraint. And so let's start with the sum of the squares. I'll represent that with s. S will be equal to the sum of the squares of those three positive integers. And so I'm going to assign the variables x, y, and z to those three integers. So the sum of the squares will be x squared plus y squared plus z squared. And so that will be our main function, or our primary equation for this optimization problem. But then we need another equation for the constraint, or the fact that the regular sum of those three integers x, y, and z is 30. So the constraint will be x plus y plus z is equal to 30. Okay, and then what we want to do is rewrite our main function, the function that is working with the value that we want to optimize, or in this case minimize. We want to rewrite that such that it is in terms of two independent variables. And we can do that by making use of the constraint. We can solve for one of these three variables in this equation, and then substitute that into this equation, and then it will just be in terms of two variables, because both equations are working with the same three variables of x, y, and z. Okay, so in the constraint, what I'll do is solve for z. That way the two variables that we will be working with are x and y, which we are pretty familiar with for working with a multivariable function of two variables. Okay, so if we solve for z here, we would want to subtract x and y from both sides of the equation, giving us z is equal to 30 minus x minus y. And so then, substituting that expression in for z in this equation will give us that s is equal to x squared plus y squared plus z squared, where z is 30 minus x minus y. Okay, and we don't have to expand this quantity. There's no reason to square it. That would just be some unnecessary extra work. So I'm going to keep it like this, because what we want to do next, now that we have a function of two independent variables, x and y, is find any critical points. We want to find its partial derivatives, set them equal to 0, and solve for x and y. And those values will correspond to the minimum value of s given this constraint. Okay, so let's find those partial derivatives. Let's take a partial derivative with respect to x of s, so sx, and looking at s here. And so going term by term, the derivative of x squared will be 2x, and then y squared is a constant with respect to x, so its derivative is 0. And then for this piece, we will use the chain rule, because we have this quantity being squared, and there is an x inside of it. So let's take the derivative of the outside function first. We'll multiply that power down, so you'll have 2 times 30 minus x minus y to the first power, because we subtract 1 from that exponent, but then you want to multiply by the derivative of the inside function, which with respect to x will just be negative 1, right? The derivative of 30 and negative y would be 0, because they are constants with respect to x, but then the derivative of negative x is negative 1, so we multiply by negative 1. Okay, so we'll simplify that later. For now, let's just move on to sy, the partial derivative of s with respect to y. The derivative of x squared will be 0. The derivative of y squared, though, will give you 2y. And then we need to use the chain rule again on this piece of the function. So take the derivative of the outside function again, and you'll get plus 2 times 30 minus x minus y. And that's to the first power, and then you want to multiply by the derivative of the inside function, which with respect to y will also be negative 1. The derivative of 30 and negative x will be 0, because they are constants with respect to y, but then the derivative of negative y is negative 1. Okay, so now we have the first partial derivatives of our function s. Now what we want to do is set them equal to 0 and solve. So let's do that. We'll have 0 is equal to 2x, and then I'm going to simplify this. You would have negative 1 times 2, which is negative 2, and then distribute that through this quantity. and you'll get negative 60 plus 2x plus 2y. And then for sy, you'll have 0 is equal to 2y, and then multiply negative 2 through this quantity as well. So you'll get minus 60 plus 2x plus 2y. Okay, so now simplifying further, back to sx, we have 2x and 2x that can be combined to be 4x. So this will be 0 is equal to 4x plus 2y minus 60. And then over here, we have two terms of 2y that will combine to be 4y. So doing that, we get 4y plus 2x minus 60. Okay, and so now we have this system of equations that we need to solve. The way I'm going to do it is to solve for one variable in one equation and then plug that into the other. And so let's solve for x in this equation. To do that, I will subtract 4x from both sides of the equation. So we'll have minus 4x is equal to 2y minus 60, and then divide both sides by negative 4, and you get x is equal to negative 1/2 y plus 15. And so now plugging that in for x in this equation, here's what we will get. 0 will be equal to 4y plus 2 times negative 1/2 y plus 15 minus 60. And then simplifying, we'll have 4y minus y plus 30 minus 60. Now 4y minus y is 3y, and 30 minus 60 is negative 30. So 0 is equal to 3y minus 30. And so then adding 30 to both sides, you get 30 is equal to 3y, and then dividing both sides by 3, you find that y is equal to 10. All right, so we have the y value. Now we need to find the corresponding x value by plugging this back into what x was equal to. So if y is 10, then here's what we'll get for x. X will be equal to negative 1/2 times 10 plus 15. Negative 1/2 times 10 is negative 5, and negative 5 plus 15 is 10. So we find that x is equal to 10 as well. And so now we have two of the three positive integers whose sum will be 30, and the sum of their squares will be a minimum. To get the last integer, we have to plug in what we found for x and y back into our constraint, right? Z is equal to 30 minus x minus y. And now that we know that x and y are both equal to 10, we know that z is equal to 30 minus 10, which is also equal to 10. So we get z equals 10 as well. And that should make sense. The sum of x, y, and z will be 30. You'll have 10 plus 10 plus 10, which is 30. And since we got these values by setting the partial derivatives of this function s equal to 0, we know that they correspond to a critical point, which in this case would be a minimum. So we know that the sum of the squares, s, is a minimum when x, y, and z are equal to 10. Okay, so our final answer here is that x equals 10, y equals 10, and z equals 10. Those are the three positive integers whose sum is 30, and the sum of their squares is a minimum. And if you wanted to calculate the sum of their squares, you could. You'd take 10 squared plus 10 squared plus 10 squared, which would give you 300. And so based off our work here, we can assume that that would be the smallest possible sum of the squares for three numbers whose sum is 30. Okay, and so our work is done here. We have found those three positive integers, but if you wanted to check and make sure that they really do correspond to a minimum on this function, you could use the second partials test. I'm not going to go through all the work from scratch here, but I will show you the completed work. And so here it is. If you use the second partials test, remember that you need to set up the formula for d. In this case, d of xy would be equal to the second partial derivative with respect to x twice for s, multiplied by the second partial derivative with respect to y twice for s, and then you subtract the mixed second partial derivative squared. And in this case, if you went through the work of setting that up, sxx is equal to 4, syy is also equal to 4, sxy is 2, so you have 4 times 4, which is 16, minus 2 squared, which is 4, 16 minus 4 is 12, and so that would be the value of d no matter what you plug into it. In our case, we found that both x and y were equal to 10, so d of 10, 10 would be equal to 12, which is greater than 0. And then if you check the second partial derivative, sxx, at those coordinates 10, 10, you would just get 4, because there are no variables there, so it's going to be 4 for all input values. but that is also a positive value, and so since both d and the second partial derivative with respect to x twice are greater than 0, from the second partials test we know that x equals 10 and y equals 10 corresponds to a minimum. Okay, but that's it for this example. Let's move on to the next one. For our second example, we want to minimize the surface area of an open box with a volume of 256 centimeters cubed. Alright, so the first thing I think we should do here, to get a better idea of what we're working with, is draw a picture of this scenario. We are working with an open box that has a particular volume, so we know that we are working with a box in 3 dimensions. So let's draw one. I'll let mine look something like this. Now it's important to remember that this is an open box, meaning that there is no top face. Okay, so imagine a cardboard box, but where the top is open. And for this box, we know that the volume is 256 centimeters cubed. Alright, so the volume V is equal to 256 centimeters cubed. And what we want to do here is minimize the surface area of this box, given that this is the volume. Okay, so we have to set up an equation to represent the surface area of this box. And then we also want to set up an equation using this value of the volume. This is what we would call the constraint of this problem. It is going to restrict or constrain the dimensions of this box. Okay, and so speaking of which, in order to create the equations of the surface area and the volume, we have to assign some variables to the length, width, and height of this box. I sort of drew it as a cube, but we don't know for sure if all the edges are the same length. Okay, so we'll let the length be x, the width be y, and the height be z. Those are the variables I'm going to assign to those different dimensions. And so then to create an equation for the surface area of this box, we have to take the sum of the area of all of the faces of the box. So I'll represent that with S. S will represent the surface area. And so going face by face, remember that there's only going to be one face of x times y, because the box is an open box. There is no face on the top. So x times y will give you the area of the bottom face, and that's it. So we want to have x times y, and then add that to the area of the 4 other faces. And the front face, as well as the back face, have dimensions of x and z. So we'll have 2 times x times z. That will account for the area of those 2 faces. And then for these 2 side faces, their dimensions are y and z. So you'll have y times z for the area of one face, but then 2 times yz for the area of 2 of them. Okay, so we'll add in 2 times y times z. And that will account for the surface area of the entire box, but of course not including a top face because the box is open. So that's going to be our main equation. This is what we want to optimize, right? We want to minimize the surface area. So now we have our surface area equation, but we also have a constraint. The volume is 256 centimeters cubed. So that means that 256 will be equal to how we would calculate the volume of this box, which would be x times y times z. The length times the width times the height. So 256 is equal to x, y, z. That is our constraint. And so our next step here is to use that constraint to help us get our main equation or our main function in terms of 2 independent variables. Because currently it's in terms of 3. We have x, y, and z throughout these terms. We just want 2. So what I'm going to do is get rid of z. I like to work in terms of x and y. So in the constraint, what I'll do is solve for z and then plug what it's equal to in for z in this equation. Okay, so to solve for z, we would want to divide both sides of the equation by x times y, and that will give us that z is equal to 256 divided by xy. And so substituting that in for z in these 2 places in this formula, we find that s is equal to x times y plus 2x times z, so we have 256 divided by xy, plus 2y times z, which is 256 divided by xy. And then simplifying, this x and this x will cancel out, and this y will cancel out, and 2 times 256 is 512. So we get s is equal to xy plus 512 divided by y plus 512 divided by x. That is going to be our multivariable function of 2 independent variables that represents the surface area of this box that we want to optimize, or in this case, that we want to find a minimum for. Okay, so our next step here is to find the first partial derivatives of this multivariable function, set them equal to 0, and solve for x and y. So let's take a partial derivative with respect to x. Let's find Sx, starting with the first term. X is to the first power, so its derivative will be its coefficient of y. So we have y, and then the second term has no x's in it, so this is a constant whose derivative is 0. And then for 512 divided by x, you could view that as 512 times x to the power of negative 1, and you would just use the power rule for derivatives on that and get negative 512x to the power of negative 2, which can be rewritten as negative 512 divided by x squared. Okay, so that would be Sx. Now let's find Sy, or the partial derivative of s with respect to y. And for the first term, y is to the first power, so its derivative will be its coefficient of x. So we get x. And then for the second term, it's the exact same derivative we just took before when we differentiated 512 divided by x with respect to x. It's just that now it's in terms of y, and we're taking a derivative with respect to y. So we'll get the same expression of minus 512 divided by y squared. And then for the last term, there are no y's there, so with respect to y, that is a constant whose derivative is 0. Alright, so those are our first partial derivatives, Sx and Sy. Now let's set them equal to 0 and solve. So we'll have 0 is equal to y minus 512 divided by x squared, and 0 is equal to x minus 512 divided by y squared. And then what I'm going to do is solve for y in this equation and plug what it's equal to into y in this equation and solve for x. So if you add 512 divided by x squared to both sides of the equation, we'd get y is equal to positive 512 divided by x squared. All right, so now I want to plug that in for y in this equation. And so doing that, we will get 0 is equal to x minus 512 divided by y squared, where y is 512 divided by x squared. Okay, so simplifying, you'll get 0 is equal to x minus 512 divided by this fraction squared. Dividing by a fraction is the same as multiplying by its reciprocal. So I'm going to write this out as 512 times the reciprocal of this fraction. So if we square the top and the bottom and then flip it, you'll have x to the power of 4, that is x squared squared, divided by 512 squared. I'm not going to bother to square that out because this 512 will cancel out with one of them. Okay, so what we're left with is 0 is equal to x minus x to the power of 4 divided by 512. All right, and now we want to solve for x, and I notice that these two terms have a common factor of x that we can pull out. So we'll get 0 is equal to x times 1 minus 1 divided by 512 times x cubed, and then we can set each of these factors equal to 0. So we'll get x equals 0, and then 1 minus 1 divided by 512 x cubed is equal to 0. Now I want to focus on this x equals 0 for a second, because it looks like we're going to have two different solutions here, but really we don't. X equals 0 doesn't make sense for this scenario, because if x equals 0, then there is no measurement for this side of the box, meaning there is no box. These three measurements, or these three values, x, y, and z, all have to be bigger than 0, okay? If any one of them are 0, you don't have a box because the volume, if you were to calculate the volume, would be 0. X times y times z will be 0 if just one of those three values is 0. But furthermore, if one of those sides is 0, it's not possible to have all the sides of the box. Okay, so x equals 0 does not make sense for this scenario, so I'm just going to X it out. We don't care about that solution. We're more worried about what's going to come from this other equation. So let's focus in on that. If we continue with this equation up here, I'm going to subtract 1 from both sides of the equation. So we have negative 1 divided by 512 times x cubed is equal to negative 1. And then if we multiply both sides by negative 512, we'll get x cubed is equal to positive 512. And so then if you take the cubed root of both sides of the equation, the cubed root of 512 is 8. So we get x is equal to 8, which does make sense, it's not 0, but we still need the corresponding y value. So we want to plug what we found that x is equal to back into what we found that y was equal to earlier. Okay, so y is equal to 512 divided by x squared, which will now be 8 squared, and 8 squared is 64, so we have 512 divided by 64. which is equal to 8. Okay, so we get x equals 8 and y equals 8. Those are two of the dimensions of the box. Technically, we don't need the third one because we want to minimize the surface area, and our surface area equation is in terms of x and y, so we could just plug in 8 and 8 in there and get our final answer. But just for the sake of completion here, for knowing the dimensions of the box, you could plug in x equals 8 and y equals 8 back into the constraint to get the corresponding value of z. Okay, we know that the volume of this box has to be 256, so if we know what x and y are, we can plug those values into this equation and solve for z. So if I do that real quick, z will be equal to 256 divided by x times y, which will be 8 times 8. So you'll have 256 divided by 64, which is equal to 4. Okay, so the dimensions of this box are 8 by 8 by 4. That would give you a volume of 256. But those x and y measurements will also give us the minimum surface area such that that volume is 256. So let's calculate that minimum surface area. We know that S is equal to x times y, so we'll have 8 times 8 plus 512 divided by y, which is 8, plus 512 divided by x, which is 8. Now 8 times 8 is 64, 512 divided by 8 is 64, so we get 64 plus 64 plus 64, which is equal to 192. And that is a value of area, right? This is surface area, so the units will not be centimeters cubed, but rather centimeters squared. All right, so 192 centimeters squared is the minimum surface area for an open box with a volume of 256 cubic centimeters. Now, if you want to check that, you could use the second partials test. And so here's what that work would look like for this example. I'm not going to spend the time showing you all of these individual calculations for this video because I mainly want to focus on the optimization problems. We already learned how to do the second partials test in a previous video, but if you were to use it on this example, the formula for D would look like this, and if you found these 3 second partial derivatives, SXX would give you 1024 divided by x cubed, SYY would give you 1024 divided by y cubed, and SXY would be 1. And so plugging in the x and y values that we found, D of 8 would give you 2 times 2 minus 1, which is 3. And 3 is bigger than 0, so then we also have to check the second partial derivative with respect to x twice. We evaluate that at x equals 8 and y equals 8, which will give you 2, and 2 is also greater than 0, and so when both d and the second partial derivative with respect to x twice are positive, that results in a minimum for those x and y values. Okay, so it checks out. The surface area that we calculated using x equals 8 and y equals 8 was a minimum. Next up, we have a tech company determines that the profit P in dollars obtained by producing and selling X smartphones and Y laptops is approximated by the model below, that being this function. Find the number of smartphones and laptops necessary to maximize profit as well as the amount of max profit. And our function P of xy is equal to 8x plus 10y minus 0.001 times the quantity x squared plus xy plus y squared minus 10,000. All right, so in this problem, we are already given the function for the value that we want to optimize, right? We want to maximize the profit, and we are already given the profit function. And it's also already in terms of two variables, x and y. And so there is no need for a constraint, which you might have noticed when we read through this problem. There is nothing that is constraining the profit here. Or at least there's nothing restricting it outside of its own model. Okay, so we don't have to worry about solving for a variable in a constraint equation and then plugging it into this one. We already have the function that we need. So to find the maximum profit, as well as the number of smartphones and laptops that create that maximum profit, we just need to solve for critical points on this function. And so let's find the first partial derivatives of this function. Let's start by finding the partial derivative with respect to x. And so going term by term here, the derivative of 8x will be 8. So we have 8, and then 10y is a constant with respect to x. Its derivative will be 0. And then we have negative 0.001 times this quantity. So this is just a constant, so I'm going to keep that outside. We're just going to multiply that by the derivative of what's inside these parentheses. So I'm going to rewrite minus 0.001. and multiply that by the derivative of x squared, which is 2x plus x times y. X is to the first power, so its derivative will be its coefficient of y. So we have 2x plus y, and then y squared is a constant with respect to x, its derivative is 0. And then of course, negative 10,000 is a constant, so its derivative is 0. Then moving on to the partial derivative with respect to y, or py, let's take a derivative with respect to y, and so 8x would be a constant, its derivative is 0. But then for 10y, the derivative would be 10, and then we're subtracting 0.001 times the derivative of what's inside these parentheses. Now x squared is a constant with respect to y, its derivative is 0, and then x times y is to the first power, so its derivative will be its coefficient of x, so we will get x plus the derivative of y squared, which is 2y. And that's it, because once again, negative 10,000 is a constant, so its derivative is 0. All right, and so now we have our first partial derivatives. Now we want to set them equal to 0 and solve for x and y. So we'll have 0 is equal to 8 minus 0.001 times 2x plus y, and 0 is equal to 10 minus 0.001 times x plus 2y. Okay, and so now to simplify these equations a little bit, I'm going to subtract 8 from both sides of the equation, but notice that you would have negative 8, and then this term would be negative, so you could cancel out those negative signs, and just have 8 is equal to 0.001 times 2x plus y. In the same way, we could subtract 10 from both sides of this equation, so you'd have negative 10 is equal to this negative value, so you could cancel out those negative signs and get 10 is equal to 0.001 times x plus 2y. Then, what I'm going to do for these two equations is divide both sides by 0.001, which is a thousandth. So if you divide 10 by a thousandth, you get 10,000, and 8 divided by a thousandth is 8,000. So we get 8,000 is equal to 2x plus y, and 10,000 is equal to x plus 2y. All right, and now these equations are in a nicer form for us to work with. And so what I'm going to do next is solve for y in this equation, and then plug what it's equal to into this one so that we can solve for x. So if you subtract 2x from both sides of the equation, you would find that y is equal to 8,000 minus 2x. All right, so plugging that into this equation, we'll get 10,000 is equal to x plus 2 times y, which is 8,000 minus 2x. And so now let's simplify. We'll have 10,000 is equal to x plus 16,000 minus 4x. And x plus negative 4x is negative 3x. And if you subtract 16,000 from both sides of the equation, you'll get negative 6,000 is equal to negative 3x. And so then dividing both sides by negative 3 will give you that x is equal to positive 2,000. And so now what we have determined here is that this tech company, in order to maximize their profit, would need to produce and sell 2,000 smartphones. Okay, but that just takes care of X, the smartphones. We still need to figure out Y, the laptops, which we can now do by plugging in 2,000 for X in this equation for what Y is equal to. So we'll have Y is equal to 8,000 minus 2 times X, which is 2,000, and 2 times 2,000 is 4,000, so 8,000 minus 4,000 is 4,000. So we have Y is equal to 4,000. All right, so that means that the tech company would need to produce and sell 4,000 laptops to maximize its profit, okay? So to answer the first part of this problem, the number of smartphones and laptops necessary to maximize profit are 2,000 and 4,000, but then we still need to find the value of the maximum profit when x equals 2,000 and y equals 4,000. So we want to plug those two values into our profit function. So let's do that here. We will have p of 2,000, 4,000 is equal to 8 times x. So 8 times 2,000 is 16,000. And then we have plus 10 times y, where y is 4,000. So that will give us 40,000. So we have 16,000 plus 40,000, which will give us 56,000. So that takes care of the first term. Then we will subtract 1,000th. That's what 0.001 would be as a fraction, times x squared. So we have 2,000 squared plus x times y. So 2,000 times 4,000 plus 4,000 squared. And then we are subtracting 10,000. All right, now 2,000 squared is 4 million. 2,000 times 4,000 is 8 million. So we have 4 million plus 8 million, that's 12 million. And then 4,000 squared is 16 million. So 12 million plus 16 million is 28 million, but then we're dividing it by 1,000, which gives you 28,000. All right, so this is equal to 56,000 minus 28,000 minus 10,000. And if you want to put the commas in there, go for it. But then 56,000 minus 28,000 minus 10,000 gives you 18,000. So $18,000 would be the maximum profit for the tech company given this model for their profit based on smartphones and laptops produced and sold. But if you want to check it to make sure that this actually is a maximum value, you could check the x and y values of 2,000, 4,000 using the second partials test, and so that would look like this. If you set up the formula for D for the second partials test in this example, Pxx is negative 0.002, Pyy is also negative 0.002, and Pxy is negative 0.001. So if you multiply those two values together and subtract this value squared, you get a constant value of 0.000003. And so no matter what you plug into D, in this case we would use x is equal to 2,000 and y is equal to 4,000, but no matter what you plug in, you will get that same value, which is positive, it's greater than 0. And then if you check Pxx at x equals 2,000 and y equals 4,000, you get negative 0.002. In fact, you would get that for anything you plug into that function because it is just a constant value, but it is less than 0 or negative. And so when D is positive and that second partial derivative is negative, that means that the critical point corresponds to a maximum. So we know that that value of profit that we calculated is the maximum profit for the tech company. Okay, and so that's it for this problem. Let's move on and take a look at our final example for this video. Hey, real quick, before we take a look at the next example, if you find my videos here at JK Math to be helpful, then I'd like to invite you to join my membership site JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out, as it's a great way to support me in the tutorials I make, as well as a great way for you to learn math better. But for now, let's take a look at the next example. Alright, so for our last example, we have a trough with trapezoidal cross-sections is formed by turning up the edges of a 30-inch wide sheet of aluminum. Maximize the area of a cross-section of the trough. And we're given a picture of one of these cross-sections of the trough. You can see its trapezoidal shape, but of course, because it is a trough, there technically is no top side, even though we can measure it. The trough is open, but the lengths of these two sides are each x, and the length of the bottom side is 30 minus 2x. And this entire length right here, or the sum of these three sides, would be 30. Right, this trough is created by turning up the edges of a 30-inch wide sheet of aluminum. So we're going to assume that all of these measurements are in inches. And you could see that it's true that these three sides add up to 30. If you take x plus x, you get 2x. Add that to 30 minus 2x, and the negative 2x cancels out with that 2x, just leaving you with 30. Okay, so that all checks out, but then you'll notice that the sides of the trough, which are being turned upwards or being bent, create some angle with the horizontal. And it's going to be the same angle on both sides of the trough. Okay, so one side of the trough is not going to be bent more than the other. They are going to be bent in the same way. They have the same angle with the horizontal. And that angle is represented with theta. Okay, so it looks like the two variables that we're working with in this case are x and theta. Right, the area of this cross-section, which is what we want to maximize, is dependent on the measurements of these three sides, which are determined by x, and the angle that the sides make with the horizontal, which is dependent on theta. So when we set up an equation to represent the area of this trapezoidal cross-section, it should involve both x and theta. And so let's work on that. To represent the area of this cross-section of the trough, we have to remember how to calculate the area of a trapezoid. And so if it's been a while since you've done that, here's how it works. If you have a trapezoid like this, where the bottom edge is A, the top edge is B, and then you have a height for that trapezoid. The area is equal to A plus B divided by 2 times H. All right, and so this is what we have to set up for this trapezoid here. But as you'll notice, we don't quite have all the measurements that we need. We do have the measurement of the bottom, which is 30 minus 2x, but we don't have the measurement of the height or the measurement across the top of the trough. And so we have to work on finding those things in order to set up an equation to represent the area of this cross section. All right, and so let's start with the height. How could we find the height, h, of the trough? Well, the measurement of the height here would be the same as the measurement of the height from the top of this edge to the bottom, right? So this measurement right here would also be h, and this measurement would make a right angle with the horizontal because we're measuring the height straight up and down. So it is perpendicular to that horizontal, creating a right angle, which means that we have a right triangle where we can make use of our trig functions. Okay, and so remember SOH, CA, TOA. This tells us how our trig functions of sine, cosine, and tangent relate an angle to the different sides of a right triangle. And so in this case, looking at our angle theta, which is this angle right here, we know the opposite side and we know the hypotenuse. And so which of these three functions, sine, cosine, or tangent, deals with the opposite side and the hypotenuse? Well, that would be sine. Sine of theta would be equal to the opposite divided by the hypotenuse. So we would say that sine of theta is equal to the opposite side of h divided by the hypotenuse x. And so we could solve for h then, right? If you solve for h here, you'll get h is equal to x times sine theta. And so that would be the measurement for the height in terms of x and theta, which is good. That's what we want, which means the only value we don't have yet is the value of b, the measurement across the top of the trough. And we know part of it, right? If you draw some lines upwards from these corners, you know that this measurement right here is 30 minus 2x. We just need to account for this little measurement here and this little measurement over here. And we can also find that with the help of a trig function, right? Because this little measurement would be the same as this little measurement down here. We could represent that with another letter. Let's call that c. And then you could relate that side to x and theta using a trig function. In this case, c is the adjacent side, so cosine is the function that we would want to use. Cosine of the angle is the adjacent side divided by the hypotenuse. Okay, so cosine theta is equal to c divided by x, which then if we solve for c, we'll find that c is equal to x times cosine theta. All right, so that is this measurement right here, and there are two of them, so if we take 2 times that value of c, and add it to this bottom measurement, we will have the full measurement across the top of the trough. Okay, so b would be equal to 30 minus 2x, and then we will add that to 2 times c, so 2 times x cosine theta. Okay, and so now we have everything we need to set up the formula for the area of this trapezoidal cross-section. We have a, we have b, and we have h, so let's set it up. I'll write it down here. We have a is equal to 1/2 times a plus b is how I'm going to write it. So we'll have 1/2 times the quantity of a plus b, where a is the bottom measurement. So we have 30 minus 2x plus b. So we have 30 minus 2x plus 2x times cosine theta, and then multiply by the height h, which is x times sine theta. So we have x times sine theta. And that right there is our area function. But we probably want to simplify it, so let's work on that next. The first thing I notice is that we have 30 and 30. Those will combine to be 60. And then we have negative 2x and negative 2x. That will combine to be negative 4x. So the area is equal to 1/2 times 60 minus 4x plus 2x cosine theta times x times sine theta. Okay, and then we can multiply 1/2 by each of these terms, resulting in 30 minus 2x plus x times cosine theta, all times x times sine theta. And because we're going to be taking partial derivatives of this function with respect to x and theta, the two independent variables, I want to expand this all the way out so that we don't have to work with any product rules. Okay, so I'm going to multiply x sine theta by each of these terms as well. So this will be equal to 30x times sine theta minus 2x squared times sine theta plus x squared times cosine theta sine theta. Now, when we go to take a partial derivative with respect to theta, we will still have to use a product rule here, but it will be less complicated than it would have been if we didn't distribute this value through this quantity. Okay, but now this is our area function, and so now that we have it, let's find the partial derivatives with respect to x and theta, and then set them equal to 0 and solve. That way we will find the critical points for this function, which should hopefully lead us to finding the maximum area. And so let's start with ax, or the partial derivative of a with respect to x. And so looking at the first term here, x is to the first power, so its derivative will be its coefficient of 30 times sine theta. So we have 30 sine theta. Then for the second term, ignore the sine theta part. You still want to keep it, but don't take the derivative of it. But do take the derivative of 2x squared. Multiply that 2 down, subtract 1 from the exponent, and you'll get minus 4x times sine theta. And then for the last term, cosine theta and sine theta are constants with respect to x. So just take the derivative of x squared, and you'll have plus 2x times cosine theta sine theta. And so that would be the partial derivative with respect to x. Now let's find the partial derivative with respect to theta. And I'm going to write that up here. We'll have a sub theta. And so starting with the first term here, 30x is a constant with respect to theta, but then sine theta, its derivative is cosine. So we have 30x cosine theta. And then the same thing here, negative 2x squared is a constant, but sine theta, you do want to take the derivative of. So we have minus 2x squared cosine theta. And then for the last term here, we will have to use the product rule because we have cosine theta times sine theta, a product of two functions in terms of theta. So let's work on that here. We'll have x squared times the derivative of this product of functions. So we'll take the first function, which is cosine theta, times the derivative of the second, but the derivative of sine is cosine, so you'll have cosine times cosine, which is just cosine squared. So I'll write in cosine squared theta, and then we will add the second function, which is sine theta, times the derivative of the first. And the derivative of cosine is negative sine. So you'll be multiplying by negative sine theta, but sine times sine is sine squared, so you could just rewrite this as cosine squared theta minus sine squared theta. That right there would be the partial derivative with respect to theta of our area function. So now what we want to do is set each of these partial derivatives equal to 0 and solve for x and theta. But real quick, before we set them equal to 0, I just want to briefly talk about what values of x and theta make sense, because that's going to be very helpful here. If you're looking at this scenario for this trough, hopefully you can see that it doesn't make sense for x to be equal to 0, right? Because if x is 0, you don't have a trough. These edges would have a length of 0, so you would just have a flat sheet of aluminum laying on the ground that has the full 30 inches. That's not a trough, so x can't be 0. But it can be bigger than 0 up until a value of 15, right? And I say 15 because if x is 15, notice what the length of this bottom side would be. You'd have 30 minus 2x, or 30 minus 2 times 15, which would be 30 minus 30. So the length of the bottom would be 0. So the upper bound of x would be 15. Okay, so x has to be between 0 and 15, otherwise you don't have a trough. You don't want the two sides to have a measurement of 0, and you don't want the bottom of the trough to have a measurement of 0. But anything else is fine. So as a side note here, we know that x has to be between 15 and 0. And in a similar manner, if you're thinking about theta and what angles would make sense for this trough, you can't have an angle of 0, right? If you have an angle of 0, that means that these sides are laying flat on the ground, so you don't have a trough. So you can't have an angle of 0, but anything bigger than 0 would be okay. They may not have the maximum area, but you would still have the shape of a trough. But then in the other direction, theta could not be a right angle, right? You could not have 90 degrees or pi divided by 2 radians, because if you had that, you also wouldn't have this shape of a trapezoidal trough. You would then have an open box. So we really don't want that angle either, okay? To maintain the shape of these cross sections of the trough, the angle of theta has to be between pi divided by 2 and 0. All right, so I just wanted to make a note of that because that will be very helpful later on. But now that we've talked about it, let's go ahead and set these partial derivatives equal to 0. So we'll have 0 is equal to 30 sine theta minus 4x sine theta plus 2x cosine theta sine theta. And then for a theta, we'll have 0 is equal to 30x cosine theta minus 2x squared cosine theta plus x squared times cosine squared theta minus sine squared theta. Now we'll come back to this equation. I want to focus on ax for right now, because what we're going to have to do is solve for one variable in one equation and then plug it into the other, which looks very complicated right now, but something that's going to be helpful here is that before we try to solve for anything, notice that all of these terms in this equation have a common factor of sine. So we can pull that out. In fact, we can pull out 2 times sine theta because all of these terms would have a common factor of 2 as well. So if we do that, we'll have 0 is equal to 2 sine theta times 15 minus 2x plus x times cosine theta. And so now what we can do is set each of these factors equal to 0 on their own. And so if you set 2 sine theta equal to 0, it doesn't matter that there's a 2 in front of it. You could divide both sides by 2 and it's gone. So really we get 0 is equal to sine theta and 0 is equal to 15 minus 2x plus x times cosine theta. All right, and so then for this equation, we only have one variable, so we could solve for it. What values of theta would make sine equal to 0? Well, on the interval that we're working with here, where theta can only be between 0 and pi divided by 2, nothing, right? Sine is equal to 0 at theta equals 0, theta equals pi, 2 pi, 3 pi, and so on. None of those angles are in this interval. So there's actually no solutions from this that we are interested in. Okay, we are not interested in theta equals 0 because if theta equals 0, we don't have a trough. But then for this equation, what we could do is solve for x and then plug what it's equal to into this equation, because it's going to be way easier to solve for x and plug that in than to try and solve for theta. Okay, so let's work on that here. I'm going to start by moving these two x terms over to the other side of the equation so that I can then pull out that common factor of x and solve for it. So if we do that, we'll get 2x minus x times cosine theta equals 15, right? I added 2x to both sides and subtracted x cosine theta from both sides. Now pulling out a common factor of x, and I'll do that over here, we have x times 2 minus cosine theta equals 15, and then dividing both sides by this quantity, we get that x is equal to 15 divided by 2 minus cosine theta. And so now that we have solved for x here, we will be able to plug that into this equation and try to solve for theta. But now before we do that, we should try to make any simplifications to this equation as well. And so let me show you what I mean by that. Notice that all three of the terms in this equation have a common factor of x. We can pull that out. There's an x here, an x here, and an x here that we can pull out and make our equation simpler, because we'll have 0 is equal to x times 30 cosine theta minus 2x times cosine theta plus x times cosine squared theta minus sine squared theta. And now we can set these two factors equal to 0 individually, right? We'll have x equals 0, and then this whole expression equal to 0, which I'll write down in a second, but we can completely dismiss this x equals 0, right? Because as we determined earlier, if x is equal to 0, we don't have a trough. Okay, so we can dismiss x equals 0. We're not interested in that solution. We're now just interested in when this expression right here is equal to 0. So that is a much easier equation to work with. Now on top of that, I'm going to make one more simplification, which may not be initially obvious that you would want to do this, but you have to remember what we're trying to solve for here. After we plug in this expression for x in this equation, we want to solve for theta, and you'll notice that we have a lot of cosine thetas that we'll be working with. We have this cosine theta, this cosine theta. Every time there's an x, we're going to replace it with this expression that has a cosine theta. So most likely we're going to want to use that to our advantage and try to isolate cosine theta. The only spot that we really can't do that is over here, where we have cosine squared theta minus sine squared theta. But thankfully, there's a trigonometric identity that can help us out here. We'll be able to get rid of this sine squared theta so that everything is in terms of cosine theta, which will be way easier for us to work with. And so the identity that I'm referring to here is a double angle identity, but we're actually going to use two different double angle identities. Let me show you what I mean. We know that cosine of 2 theta is equal to cosine squared theta minus sine squared theta. So you could rewrite this expression with cosine of 2 theta. The only problem is that we don't want to have a double angle, right? We want everything to be cosine of theta, not cosine of 2 theta. But there is another identity that cosine of 2 theta is equal to 2 times cosine squared theta minus 1. That one is a lot nicer. We have a cosine squared theta, but that's okay. We can probably work with that as opposed to a double angle. So what we can do here is this. We can say that this expression, cosine squared theta minus sine squared theta, is equal to cosine of 2 theta, which is also equal to this expression. We can just replace this expression with that, and we will no longer have any sines in our equation or any double angles. Okay, so that's what I'm going to do here. I'm going to rewrite this to be 0 is equal to 30 times cosine theta minus 2x times cosine theta plus x multiplied by 2 cosine squared theta minus 1. And now we're ready to go. We can now plug in what x is equal to into this expression, and we should be able to solve for theta. So let's work on that now. I erased a lot of my previous work because we're going to need a little bit of space here. Let's plug in this expression, 15 divided by 2 minus cosine theta, in for these two x's, and we'll get 0 is equal to 30 cosine theta minus 2 times x, which is 15 divided by 2 minus cosine theta, times cosine theta, plus x, which is 15 divided by 2 minus cosine theta, times 2 cosine squared theta minus 1. And now what I'm going to do here, to make this equation easier to understand or easier to see how we're going to solve it, I'm going to let cosine theta equal a single variable. All right, I'm going to let w, you could pick any letter you'd like, I'm going to use w, I'm going to let that be equal to cosine theta. And then this equation will be a lot easier to understand, and I think you'll quickly see what we can do to solve for cosine theta, or in this case w, and then ultimately theta. So doing that here, we'll have 0 is equal to 30w minus 2 times 15 is 30 times cosine theta, so you'll have 30w divided by 2 minus w plus 15 divided by 2 minus w, but I'm going to move this quantity into that numerator as well. And so you'll have 2 times w squared minus 1. All right, so we have 15 times 2w squared minus 1 divided by 2 minus w. And now what we want to do, since this is all set equal to 0, if we get these three terms to have the same common denominator, we can just completely remove it. We can multiply both sides by that common denominator and be able to solve for w. And these two terms already have a common denominator of 2 minus w. So really all we have to do is multiply this term of 30w by a form of 1 of 2 minus w divided by itself. So I'm just going to do that right here in this step. I'll multiply this by 2 minus w divided by itself, which means that we can combine the numerators here and then multiply both sides of the equation by that common denominator, and it will be gone. Okay, so if you do that, all you'll be left with is 30w times 2 minus w, so 30w times 2 minus w, minus 30w plus 15 distributed through this quantity, so we have 30w squared minus 15. Okay, so once again, now that all three terms have a common denominator, we would be able to combine the numerators and then just multiply out that denominator since everything is equal to 0. And I know that that seems a little bit weird because we might be eliminating a potential solution for w by doing that, but this is a little bit different than if we were solving for all of the potential critical points. We're just trying to solve for at least one here, because usually in optimization problems, there's just one particular value that you're looking for that will correspond to what you're trying to optimize. All right, so don't worry too much about eliminating a variable in this case. Okay, but then moving on, we still have some more simplifications that we can make. You can multiply 30w through this quantity. So you'll have 0 is equal to 60w minus 30w squared minus 30w plus 30w squared minus 15. And now some nice cancellation will occur. We have a negative 30w squared and a positive 30w squared. Those will cancel out. And then we have 60w minus 30w, that's positive 30w, and then just this negative 15 on the end. So if I continue my work over here, we'll have 0 is equal to 30w minus 15. Add 15 to both sides, and you have 15 is equal to 30w, and dividing both sides by 30 gives you that w is equal to 1/2. But remember, we let w be equal to cosine theta, so really this is cosine theta is equal to 1/2. And for this range of values for theta, cosine theta is equal to 1/2 at pi divided by 3. So that would be our solution here. Theta is equal to pi divided by 3. Cosine will be 1/2 at that angle. All right, and so that's one of our values, but remember, we need a value of both x and theta in order to maximize the area of this cross-section. That area is dependent on both x and theta. We have the value of theta, now we just need x. So you want to plug pi divided by 3 into this expression for x that we found earlier, and we know that cosine of theta, or in this case cosine of pi divided by 3, is 1/2. So doing that work, we will find that x is equal to 15 divided by 2 minus 1/2, which will be equal to 15 divided by 3/2. And 15 divided by 3/2 is the same as 15 times 2/3. And 15 times 2 is 30, divided by 3 is 10. So we get x equals 10. And in this case, that would be 10 inches, since x corresponds to measurements for the aluminum sheet. All right, and so now we have what we need. We have the x value and theta value that correspond to a critical point on this multivariable function representing the area where we should get the maximum area for the cross-section of the trough, which means our last step here to maximize the area is to find the area. We want to plug these two values into our area formula. So let's do that here. We will have that the area A is equal to 30 times x, so 30 times 10, times sine of theta, or pi divided by 3, minus 2 times x squared, or 10 squared, times sine of pi divided by 3, plus x squared, so 10 squared, times cosine of pi divided by 3, times sine of pi divided by 3. Now simplifying, 3 times 10 is 300. Sine of pi divided by 3 is the square root of 3 divided by 2. And then we are subtracting 2 times 10 squared, which is 200, times sine of pi divided by 3. So we're multiplying by the square root of 3 divided by 2. Then you'll have plus 100 times cosine of pi divided by 3, which is 1/2. And then again, sine of pi divided by 3 is the square root of 3 divided by 2. And so simplifying further, 300 divided by 2 is 150. So we have 150 square roots of 3 minus 200 divided by 2 is 100. So minus 100 square roots of 3 plus 100 times 1/2 is 50, divided by 2 again will give you 25. So we have 25 square roots of 3. So 150 square roots of 3 minus 100 square roots of 3 gives you 50 square roots of 3, but then plus 25 square roots of 3 gives you the final answer of 75 square roots of 3 inches squared, right? This is a value of area, and the sheet was measured in inches, so we know that the area will be inches squared. That is the final answer to this example. That is the maximum area for the cross-section of that trough. And as an approximate value, 75 square roots of 3 is about 129.90 and some more decimals. Okay, but real quick, if you wanted to check it, if you wanted to make sure that this is a value of maximum area, you could use the second partials test for x equals 10 and theta equals pi divided by 3. If you set that up for this example, here's what you would find. I'm not going to go over every single step of the process here, but the formula for d would look like this. Normally you have x and y, but since our variables are x and theta, it looks like this. d of x theta will be equal to the second partial derivatives with respect to x twice times the one with respect to theta twice minus the mixed second partial derivative squared. These are the different expressions that you would get for those second partial derivatives. But then plugging in 10 for x and pi divided by 3 for theta, you get this expression, which simplifies to 450, which is positive or greater than 0, and then the second partial derivative with respect to x twice, evaluated at those values, is negative or less than 0, and so when d is positive and this partial derivative is negative, via the second partials test, that corresponds to a maximum value. So the area that we calculated is indeed the maximum area for a cross-section of the trough. Alright, but with that, that is it for this example, and this was also the last example for this video. But if you do want to get some more practice, I have another available on my membership site, so if that's something that interests you, feel free to look into becoming a member. You can find all the details on my website at jkmathematics.com/plus. If you have any questions, please let me know in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.